Hello everyone, welcome to part 2 of lecture 23. So, we discussed about the snow depth estimation in the previous part. Now, in this part, we will try to discuss about the density, permittivity and the other parameters, how we can estimate using the satellite remote sensing. So, when we talk about the density, which is a fundamental property of snow defined as the mass of the snow per unit volume. It varies significantly depending on the snow's age, condition and other factors. Fresh dry snow has relatively low density, while older or wet snow can be significantly denser. Because you can just try to visualize this when you are having the snowfall, right. So, these are the fresh snow or the ferns which are accumulated here. Slowly what happens, on top of it there will be another accumulation of snowfall, right, and these will be the overburden to this first layer, and because of the increased temperature and pressure there will be solidification, right, they will be more compact. So, when we talk about the fresh snow, they have very low density compared to the denser one or the older one. So, the factors which affect the snow density are the snow type, temperature, wind, metamorphism, compaction and the liquid water content. So, what is the liquid water in this particular snowpack? That also defines the density, what will be the density in this particular snow. Similarly, we have permittivity. So, it is a measure of its ability to store energy in an electric field, is highly dependent on its state, whether it is a dry snow or wet snow, and the presence of liquid water. So, because all are related, so whether it is dry or wet snow, we have wet snow, then we have more liquid water content. So, but to understand its state and the presence of liquid water is very important. Dry snow, primarily composed of ice and air, has a low permittivity than wet snow, which includes liquid water. And similarly, we have the factors which affects the snow permittivity. So, they are snow density, liquid water content, temperature, snow type and snow microstructure. So, when we talk about the microstructure, means the crystal size and the orientation, that also defines the permittivity. Then comes the wetness. So, it is also known as the liquid water content, refers to the amount of liquid water present within a snowpack. So, this particular image is just to explain that this particular ice has more water content. So, visually you can identify, but when we talk about the liquid water content present in snow, whether a snow is dry or wet, we need an instrument to measure it, right. So, this particular image is just to explain how these two are different. So, here you can easily see that this is the wet snow, right, but when we talk about the snow in ideal condition, you need an instrument to measure the wetness. It is a crucial factor in understanding snow hydrology, seasonal snow change and the regional climate variability. The presence of even a small percentage of liquid water significantly alters the physical, thermal and electromagnetic properties of snow. And here the factors which affect the snow wetness, they are temperature, solar radiation, air temperature, snowpack density, precipitation, slope and aspect. Because we are talking about the snow wetness. So, the wetness will increase when we are having more energy into the system. So, the temperature is very simple to understand. The solar radiation will play a role here, whether this particular area or this snow pack will receive more energy or less energy. Air temperature, what is the ambient temperature, then density of the snow, the precipitation, the liquid precipitation, because we all know that the precipitation, the water droplets, they also bring energy along with them, that will also change the liquid water content of this particular snowpack. and the slope and aspect, because depending upon the topography the flow will happen. So, if there is a precipitation, whether it will be here or here, it will be defined by the slope or the gradient, right. So, the geophysical properties of snow are essential to study the snow or glacier system and can be used as an indicator for any related hazard, because the stability, what is the status of that glacier, that will be defined by these geophysical properties. The important geophysical parameters of snow like dielectric constant, density, liquid water content play a vital role in avalanche study, hydrological modeling and flood monitoring. Our study attempts to model the geophysical properties of snow such as dielectric, density, wetness using Sentinel-1 and Prisma data, which is a hyperspectral data set. The inversion model was developed utilizing dataset for two distinct glacier regions in Sikkim Himalayas. So, we have South Sikkim and the North Sikkim. So, both the areas we have considered in our study, and then we have developed a inversion model. Snow is a heterogeneous mixture of air, ice and liquid water. To characterize snow, it is important to understand the dielectric properties of the mixture. So, the snowpack. The earlier studies state that liquid water content, permittivity and density are related in nature and are based on the linear mixture of the dry snow dielectric constant, right. With the rise in dielectric constant generated by liquid water content in the snow as explained in this equation 1, 2, 3 and 4. So, you can see this particular relationship is very important. So, I will strongly suggest please go through the papers that I have listed at the end of this lecture to understand the different methods used in the snow geophysical parameter estimation using hyperspectral, multispectral and microwave remote sensing data set. So, here you can see the study area. All these star marks are our field location where we have investigated. So, these are some of the field photographs, right, and this is again the South Lonag Lake, and this already you have seen in 2015, 16, 17, 18, 19, 20 till 23 how this is changing after the South Lonag Glacial Lake outburst. So, for this estimation we have used this particular flow. This is the broad methodology. So, here we have applied the orbit file correction, then radiometric calibration, burst removal, covariance matrix, multi-loop speckle noise reduction, terrain correction, and then we have used the Stokes parameter, which are further used to estimate the geophysical parameters of the snowpack. So, here we have also used a snowfolk, which is in situ measurement, which can measure the permittivity, wetness, density. So, here you can see the snowfolk data format. So, we have a snowfolk instrument which can measure the wetness, density and the permittivity in the field. The Sentinel-1A with descending pass acquired the data on 6th April 2022, while the field in measurements we visited that area on 7th April 2022. So, there is 1 day gap because it is very difficult to match the time on these rough terrains. So, the level 1 SLC product of Sentinel-1A dual polarimetric C-band SAR dataset have been used in this particular study. And as I mentioned earlier, the Prisma hyperspectral sensor was also used here, which is from the Italian Space Agency, and which has 240 contiguous spectral bands between 400 to 2500 nanometer, and 30 meter spatial resolution is there for this data set. This table explains the different snow grain sizes that we have considered, right. So, a novel method for dielectric density and wetness estimation has been developed using the Sentinel-1A dual polarimetric data. So, here as I mentioned in the previous slide, these are the processing steps that we have used to generate the Stokes parameter, right. To align the pixel along the precise track of the satellite, in orbit calibration is performed by applying Sentinel precise orbit state vectors. Calibration is the procedure that converts digital pixel value to radiometrically calibrated SAR backscattered value. So, here you can see. Then burst removal, which is here, is a broader noise removal that eliminates low intensity noise and invalid data or scene edges. Then comes the covariance matrix generation. So, it is the vectorization of the scattering matrix, right. Then comes the multi-look. So, it produces a product with a nominal image pixel size averaging over range and azimuth resolution cell, right. Then we have done the speckle noise reduction, terrain correction. These are the standard procedure. Then the novelty comes here in the Stokes parameter generation. So, in the field you can see this is the snowfall instrument that is being used to generate the in situ measurement at different depth, right. So, this is one of the representative photograph, but we have many vertical section that we have considered in the field. So, this is another photograph. You can see this is the location, this is the field photograph, right. And here in 2022 again we have visited this in the south Sikkim. So, this is the paper I was talking about, that inversion model for snow geophysical parameter estimation using Sentinel-1 Stokes parameter. This is a state of the art inversion model which is developed using Sentinel-1 Stokes parameter to estimate the snow dielectric, right. So, here you can see how we have formulated the dual pole Stokes parameter. So, as I mentioned, the Sentinel-1 dual pole SLC data was used, and after doing all the processing it was saved as complex output in order to obtain two element complex vector called coherency matrix, C2 matrix, right. So, here you can see the C2 matrix has been calculated using this equation, and the Stokes vector for the scatter wave is entirely determined from the C2 matrix as following 2 and 3 equation, right. So, here you can see the T3 matrix of quad pole into dual pole Stokes vector is shown in this particular equation, where T11, T22, T33, right. So, these are the elements of the T3 matrix. Upper sign of H transit and lower for V and theta misalignment between radar coordinates and the scene symmetric axis. In quad pole, under the assumption of the reflection symmetry, the coherency matrix is written as this, right. And this matrix is used to map the dual pole Stokes vector using the general mapping of reflection symmetry. So, this is the further derived equation from the 5. So, similarly, the mapped Stokes vector for the tilted polyphase is given as equation 7. After rearranging this, we have equation 8 which can be used to calculate the theta value, right. So, here S1, S2, S3, S4 all are used. So, theta value can be calculated using equation 8 using dual pole Stokes vector for Sentinel-1. Now, replacing theta in equation 4 and arranging equation 4, we obtained our desired equation that we propose as a novel inversion model based on Sentinel-1 derived Stokes vector. So, this is the one, right. So, it is independent of surface roughness and depends only on dielectric and local incidence angle. Hence, a new inversion model is formulated based on the Stokes parameter to obtain dielectric values. So, this is the novelty in this particular work. The efficiency of this model was tested using Sentinel-1 derived Stokes parameter. The permittivity related to snow density is determined by Loenga's equation. The earlier study states that liquid water content, permittivity and density are related in nature and are based on the linear mixture of the dry snow dielectric constant, right. With the rise in dielectric constant generated by liquid water content in the snow, which is shown in equation 1, 2, 3 and 4. Further, for the snow wetness, the end member from GHU spectral library was extracted and then resampled to the spectral resolution of Prisma data, which is a hyperspectral sensor, and using spline we have resampled it. The atmospherically corrected Prisma hyperspectral cube is subjected to the dimensionality reduction to extract the most informative bands corresponding to GHU spectral library, because this is the library which we have used. So, then we can calculate the NDSI. The soil moisture assessment, the trapezoidal or triangular feature space based on the land surface temperature, the LST, or NIR reflectance and the NDVI have been utilized extensively in the literature. The response of the near surface snowpack can be studied using spectral data in the visible and infrared band in an integrated framework for monitoring the liquid water content in the snowpack. The approach relies on the physical interaction between light and snow, where snow properties such as grain size, liquid water content affect the spectral reflectance observed in the electromagnetic spectrum, which is in the visible and near infrared region, right. So, how the surface is reacting with the change in the grain size or the wetness, that has been studied here. So, the NIR band sensitivity to snow grain size is identified to be 1.03 micrometer. So, this is very critical, which is opted for snow surface wetness estimation, and then we can calculate. So, the liquid water content, permittivity and density are among the snow geophysical parameters coupled in nature. Snow dielectric and density are estimated using the state of the art empirical models. The least square solution for snow dielectric was found using the corresponding value of liquid water content. Further, the derived snow dielectric calculates snow density using the model defined by Loenga. So, this is Loenga 1965 and he has given this particular relationship, and this is very useful. So, based on that you have to identify different geophysical parameter. So, each component of S1, S2, S3, S4 that we have mentioned in equation 10 is considered non-zero when the Stokes vector for Sentinel-1 is calculated. The theta is the angle formed by the scattered symmetric axis and the radar transmit polarized signal axis. Since the study area is hilly terrain, hardly it will have such values. The histogram plot for theta is seen in figure and is observed as non-zero. So, here you can see. So, the proposed inversion model based on Sentinel-1 derived Stokes parameter or the Stokes coefficient is applied to the proportion of the Sentinel-1 seen acquired on 6th April 2022. The model equation shown in equation 9 is solved to retrieve the dielectric values and subsequently density can be estimated. So, here you can see the dielectric density and the wetness that has been estimated for the Rathong glacier region. So, here you can see the box plot. So, the map of the scene shown here also covers Rathong glacier and the density of the glacier ranges from this to this range. Based on the density range and the snow can be classified into 4 categories: fresh, settled, old and moist. The measured snowpack in the field has been determined to be settled, old snow and moist. It is observed from the field data because we have the field information that reflects the continuous nature of snow transformation, which is very common in glacial environment. A few statistical analyses have been performed to check the efficiency of the proposed inversion model, and the box plot for the model, which is here, it shows the efficiency of this model. Snow dielectric density and wetness are compatible with the measured values according to the median seen from the box plot. You can see here. It is also evident from the box in the plot that the model parameters are overestimated. The linear fit between the model and measured value is shown in the table along with its scale and bias parameter. You can see the graph of the correlation between the modeled and the measured parameters are shown in the figure. The estimated values of the dielectric density and liquid water content are found in according to the measured values, right, and where we have got the R square which is greater than 0.7. Due to the absence of intermediate values, it can be observed in the box plot that all the parameters are deviated from the standard normal distribution. So, here this is our model. These are the earlier models which have been developed by various researchers, and here it significantly tells us that our model has improved the efficiency in estimating the geophysical parameter. So, here you can see different spectra that have been considered. This you have seen in the different lecture also. So, to mask the glacial lake from the NDSI derived snow cover map, spectral unmixing is performed using the GHU snow spectral library. The resulting abundance fraction map shows the abundance of snow in each pixel in the range of 0 to 1. This study considered a threshold greater than or equal to 0.5 to be identified as snow covered pixel. The end member derived from the snow pixels are identified as coarse, medium, fine and frost. Concerning the GHU snow grain spectral library using a widely accepted and reliable SAM method. So, here you can see using this we have also estimated the wetness, dielectric and density. So, the wetness of each snow grain size agrees with the theory that the snow grain size increases with increasing water content. Through a process known as wet snow metamorphism, water functions as a lubricant helping the snow grain bond and round. Grain clumps come together and form larger grains due to the capillary action produced by the liquid water. Additionally, this procedure promotes quicker melting and refreezing cycle, further enhancing grain growth. The firn density, which is the fresh snow, converted to glacier ice density equal to this 830 to 927 kg per meter cube. The proposed model can forecast the density of the Indian Himalayas region within the permissible range. So, I will strongly recommend these papers to read to understand various methods which have been used in estimating the snow geophysical parameter, right. So, these are the references. This is from my research group and you can see all the details which is relevant for the snow geophysical parameter estimation using the satellite remote sensing data set. So, these are some of the additional information. Here you can see some of the other aspects, how you can investigate the Indian Himalayas and with different objectives. This is my research group. So, you can see different members here, some of the existing ones, some of them are graduated. So, all of them have contributed and their studies are considered in all these lectures. And some of the field photograph, particularly while doing the field investigation, you can see here. So, this is the glacial snout. Thank you very much.